So all of you know, I think the person who sells milk, no, he will boil it, then he will add to warm water. So then what will be very little bit difficult to identify that one. If you add just the warm milk to warm water, no, it will not mix up properly. I think there's a trick, the trade thing. I'm not milkman. I just got an idea that one after interacting with persons who are selling milk. No, there's a trick what they use. So let this be water. So definitely I want to earn more profit. If I pure milk, if I sell it, I'll get less profit. No, so therefore let me add some water. So I'm very, you can say, greedy person. I'll add 1 kg water. So what is the temperature of this? 20 degrees Celsius. Where do I mix up this? Where do milk will be there? In some vessel, no? Where do water? It will be in some vessel. It is what? Okay, now I'm going to mix up them in some vessel. So what actually happens is this is practically. So usually on paper we do it. Now, okay, milk and water. This milky water, milk plus water it is. So 1.4. So this will become 2.4. What is the final temperature? Okay, we do on paper, but practically the hot milk, so this will be water. It will be there in one vessel. Fine. So this is the, okay, we'll take some, it'll be easy for me. Okay, there's the water. Yeah. And there's a water, 1 kg, temperature 20 degrees Celsius. Here I'm going to pour that milk. I'm going to pour that milk here. I'm going to mix up. There's a vessel in which I'm going to mix up. Fine. So I'm going to add that milk here. What is the temperature? 80 degrees Celsius. This is 1 point, what will take it? 1.5. So 1.5 kg. Tell me, like here, both will get mixed up. Both will get mixed up, and we do get like this. Huh? There's a mixture. Why color will not come? Okay, now at least about imagine, come out of dream world, be practical. So there's a milk, 1.5 kg. No, this is the milk plus water. I want this temperature. Even this vessel is having a some mass. Okay, definitely this will be, let it be 0.4 kg vessel. So what is the temperature of water? That will be the temperature of this vessel also. Will you agree this? So when you pour this hot milk 80 degrees Celsius to this, who will absorb it? Only this water, or water come plus vessel? Both will absorb it, no? So the final temperature, what you calculate on paper and practically what you do, little bit different. So let's do one thing. So there's a mixture. So what is the equation? We'll write it. Heat lost by milk is equal to heat gained by water plus vessel. Heat lost by the milk, 1.5 specific heat of milk into final temperature T minus 80. So sorry, 80 minus T, heat lost, no? Yeah, heat lost by milk. What is SM? Specific heat of milk. Okay, we'll put it some 1.4. Till here, no problem. What about heat gain by water? Specific heat of water 1 SW T minus 20. 0.4 specific heat of vessel T minus 20. What is 0.4? Mass of the vessel. So here specific heat of water is 1. So this will be 0.4 SV T minus 20. So tell me what is the biggest headache? Mass of the vessel, mass of the empty vessel, I know it, 0.4 kg. What is 0.4 kg? Mass of vessel. What is the biggest problem? What is the specific heat of vessel? In general, I write specific heat of. Tell me what is the problem we are going to face here now. Sir, what is the specific heat of vessel? It is made up of iron. I'll look at the chart. Then what we get? Specific heat of iron. I'll substitute here. Are you sure it is pure iron? Are we sure that is it a pure iron? Are we sure is it pure iron? Definitely no. Will I agree? So what is this vessel made up of? Again, we should go for the manufacturing, where it is manufactured. Then we should ask him, what all you added in this? What all you added in this? So definitely what happened, he will be, what you'll reply. Okay, well, already you purchased vessel, finish or no? Why you are troubling me? Because definitely what will happen, many impurities will be present. So what is the biggest problem? That SV of the vessel is the biggest problem. Specific heat of vessel is a big problem. Will I agree this? So I should overcome this one, no? So fine, okay. We are studying calorimeter, but practically when you go, no, anybody, can you say in the steel vessel, will you say that exactly how much of iron, zinc, how much of aluminum, copper will be there? I think when you measure that steel containers for the kitchen, no, will they mention, okay, how much of iron, how much of, say like a copper, how much of zinc and how much of aluminum is present in that? Nothing, no information. Even if you want to find out, not possible. Even what we can say, only mass we can predict, but what are all the compositions? This is very difficult. Specific heat of vessel, very difficult quantity to measure. Very difficult. So how to solve this problem? So what we should know, that vessel, what all elements it is present, how many different materials are present. We should know their mass, everything. I think it's a big headache. We have to do big research for that. Definitely we have to spend lakhs of rupees for that. Maybe it may go to 20, 30, 40 lakhs. Better to avoid this experiment. So if you go for industry, they can't, without vessel, they can't make. So they need. So therefore, they have brought an alternative method. So without this SV exact, because see, now you can ask question. Sir, what is that? This one, I'll use thermometer. I'll use thermometer because I must know even what amount of use. I'll use thermometer. I'll measure the temperature. Problem solved. No, why I should fight so much here? Because even I should know like what amount of heat is absorbed by that particular syrup. No, so if I mix up syrup, so therefore this vessel becomes very important. Its details are needed. So for that, what pen will go for water equivalent of calorimeter. That is the only thing. That is the only alternative available here. So therefore, now where do I mix up here? This is called like a, this vessel is called as a calorimeter, where I mix up two different liquids. No, that particular vessel is called as a calorimeter. What actually calorimeter made up of? It's a cylindrical vessel. Outer surface, I'll give wooden coating. For outer surface, Let me go for some 3 dimensional. It'll be easy for us. Yeah. It'll be like this. The outer surface will be given wooden coating. Why wooden coating? Usually calorimeters are made up of copper only. Like this, some wooden coating will be given for it. This is basically a copper. I'll write it here. Copper. This will be wood. Then I will, if you go for plane diagram, I can show it. A lid will be there. Again, it will be made up of wood. The coating will be there like this. Why wood? To insulate it. This lid will be made up of wood, strictly. You just type in Google, no, you can see the calorimeters. So this will be lid. I can because if I pouring liquid water pen, I'll just open the lid. Then I'll pour the liquid immediately. I'll close it. So this will be the lid. This one. Or to measure temperature water pen, we do make some hole. Through that hole, I can insert a thermometer. So this what? This one. So again, what we are bothered, there's a copper, wooden coating, this and there's a lid. So the here inside here, what happened? That particular liquids which I want to mix up, they'll be placed here. Then after mixing up properly, then I'll measure the temperature of mixture using this thermometer. So I'll open the lid, I'll pour the liquids which to be mixed. Then one spoon will be there, stirrer will be made up of wood. With that, I'll mix them properly. Then I'll put a thermometer, I'll measure the temperature of mixture. So what is the problem here? This copper which is there, it will also absorb heat. So it should also be taken into picture here. So how to calculate the specific heat of this particular thing? Usually this particular vessel, no, this particular will have a mass MC, I'll write it. This will have a specific heat SC. So I can never find out specific heat capacity of this calorimeter. Here I took SV. Here I'm writing SC, that one. Specific heat of calorimeter. This will be very difficult quantity to measure. Somehow I can measure mass. This will be very difficult. How to overcome this? So what I do is like, I'll just take an empty calorimeter. I'll just show only copper one. The wood one, I'll not show it. This is an empty calorimeter. What is the mass of this? I'll measure MC. And specific heat, we don't know that one. I will take equal amount of water. So there's a water. What was the temperature of this? Say like a 15 degrees Celsius. Then there's a water, 15 degrees Celsius. What is MW? The mass of the, what is the mass of calorimeter? That much amount of water is what I'm going to take it. I'll supply heat for both. Same amount of heat will be supplied. Then finally, what I see that both will acquire same temperature. This empty calorimeter will acquire same temperature, say 20 degrees Celsius. This MW amount of water will also acquire the same temperature. Empty calorimeter, I'm not going to pour that water. Tell me like, yeah, uh, what you can say that one. What are equal? So let's do one thing. Q equal to MCSC final temp. Oh, okay, 20 minus 15. Then similarly for water, mass of water, specific heat of water, 20 minus 15. I'll equate both. MCSC is equal to MW by SW. What is the specific heat of water? 1 calorie per gram per degree Celsius. So this is what in the books now they call that as W. This everything. This MW is called as W. It is called as water equivalent of calorimeter. Of course, it's a wrong unit, no. So what is the water equivalent of calorimeter? So I'll just write it. So two grams. So how much of water I took? 2 grams of water. So what is the mass and specific heat of this calorimeter equal to 2 grams of water? It's a wrong unit. Still, I'll express like this only. This call okay, water. What is this W should call? Water equivalent of calorimeter. That's why when you go and purchase calorimeter, 10 gram calorimeter, 20 gram calorimeter, 30 gram calorimeter. So what is the 10 gram, 20 gram? Not the mass of calorimeter, water equivalent of calorimeter. So we need not to bother like, so like what is the specific heat of calorimeter? What that material made up of, we don't know. I say copper, but will it be pure copper? There'll be around some 10, 15 impurities are there. What is mass of impurities? We don't know all. So just this mass and specific heat of calorimeter, we are expressing in terms of amount of water. So therefore we'll call that as water equivalent of calorimeter. I'll just give one numerical so that'll be easy for you instead of telling all this story. So we have water equivalent of calorimeter. It is equal to say 5 gram. Then I have a liquid. (60 gram), temperature say like a 50 degrees Celsius, specific heat, let it be 2. I'm going to pour another liquid. Temperature of this, let it be 30 degrees, mass 20 gram, specific heat of this, let it be 1.5. What will be the final temperature of the mixture? Same problem. We will look at that water equivalent of calorimeter, what to write. So both will get mixed up. Green color needed. Okay, this will be the mixture, no? What is the temperature of mixture? Okay, now who will gain it? This liquid 2 and the calorimeter will, so like who will gain it? I will do one thing. It will be much easier for you. Who will gain it? The liquid 1 and calorimeter. What is the temperature of liquid? That will be the temperature of this calorimeter. And who will lose it? This second liquid. So now heat lost by second liquid, heat lost by liquid 2 equal to heat gained by liquid 1 plus heat gained by calorimeter. Heat lost by this mass specific heat 50 minus T. Heat gained by liquid 1 M1 S1 T minus 30. Mass of calorimeter, specific heat of calorimeter, T minus 30. We don't know this one. What to do? What shall I do with this? Water equivalent of calorimeter. What is W? W is water equivalent of calorimeter is 5 gram. So in place of MCSC, I should write 5. Problem solved. So what is M2? This will be 20. 20, it is not 2. 20. Specific heat of this is 1.5. M1 is how much? 60. This is 2. In place of MCSC, I should just write only 5. That is enough. I think wrong units, no? Will agree?
Yes, sir.
Wrong units. Water equivalent of calorimeter. What I should write? I should write the units. So this is like a thermal heat capacity, no? It should be. But still, I'll express in grams. Wrong units are used. Water equivalent of calorimeter. So in place of, is it, sir, mass of calorimeter you are writing? No. Mass into specific heat of calorimeter is what? 5. This is called like a water equivalent of calorimeter. Water equivalent of calorimeter. Wrong units. Expressed in grams only. And it is, we know that it's a wrong unit, and we know that why we are doing is because the water is most easily available in any part of the world, no? So they have made that as a standard. I would have picked up some other liquid, but since water is widely available, no, so therefore with respect to water we are taking reference. So now solving for T will get the required answer. So you got the idea now, water equivalent, nothing big, no? We should understand, we should put effort to understand the things going on. So students, what happened? They want to write this equation without all this background diagram. Not possible. There is a wrong way of learning things. When physics becomes mathematics, then you are going to see the hell. When you introduce drawing to the physics, then you are going to really enjoy the physics. Okay, this is about the water equivalent of calorimeter. A water equivalent of calorimeter is negligible. Means what shall I do? I need not to bother this quantity. I need not to bother this quantity. Are you getting now? Water equivalent of calorimeter, if they give, means even the calorimeter also will be involved in heat exchange. Even empty calorimeter can be at higher temperature. I'll pour the warm liquid. Then the calorimeter will give heat to that substance. It can happen. Now, who is gaining it? Calorimeter and this liquid one. Okay, we'll go for now change of state in matter. So till now what we studied, if a body